So mechanical energy, we're going to use the letter E, is defined as the sum of the potential and the kinetic energy. Of an object. So here we go. E, that's the mechanical energy, equals the sum of the potential plus the kinetic. Remember, the potential is calculated by mass times gravity times height, and the kinetic energy is what? 1/2 mv squared. And the total work now required, we'll take a car on incline now, is the change in the kinetic, the change in E. That's what I'm going to write. Which is E final minus E initial. Now, if you remember last class, we did the car trying to pass another car, but it was on a flat road. Well, let's do the same story here. But let's say the road has a pitch in it, has an incline. So here we go. You're trying to pass a car. You're going up the hill. The truck in front of you is going really too slow. Angle is 15-degree angle. There's you here in your car, going the speed of 50 miles per hour. And there's a truck here, a U-Haul, whatever it is. And you're trying to pass that. So you step on the gas and you pass it, that's you. And now your velocity here is 60 miles per hour. So your speed increased, bless you. You also went uphill. Okay, you decide. Do I want to give you the height or the distance? Which one you want to be given? You want to be given the length of the road, how long it took you to pass the truck, distance? Pick a number. How many meters?
20.
Boy, you gunned it. 20 meters is a short gap too. Let's say 50 meters. 20 is too short to pass that truck there, to get the car to speed. Could be done, it can't be, but you're cutting the other driver off. Boom, boom, you start to zip and you go around. 20 meters, the length of this room. So, a little bit longer than this room. So from the time you step on the gas and you're gonna cut that U-Haul there, jump in front of them, pushing it there. 50 meters still probably short, but that's fine. I need to know what this height is. How do we find the height? This has now become trig. This is the 15, this is the hypotenuse. What's this side? This is the adjacent. This is the opposite. This is the hypotenuse. Quick trig lesson here. Opposite, adjacent, we use X. Opposite, we use Y. Hypotenuse, we use R. And this is theta. Remember this? If you took trig, Sakatoa. What does that mean? That's some Indian chief, by the way, the name. I don't know what his claim to fame is, but everyone used that. We can research that and see. The sine of theta is thus O for opposite, H for hypotenuse. C is for cosine. It's the adjacent over the hypotenuse. And T for tangent is the opposite over the adjacent. Since I need to know what the height, I need to know what H for this example is, the height, because the potential energy depends on the height. So I have the opposite and the hypotenuse. I have to use which one? The sine, because sine uses opposite and hypotenuse. So if I use that here, we go sine of 15 degrees equals the side that's opposite to the hypotenuse, which is 50. Now I can multiply both sides of the equation by 50 to get rid of the fractions. And what's the height? 50 times sine 15. So you climb about 13 meters. By the time you pass that truck, your car actually risen about 15 meters from this level. If I use this as reference, you're 13 meters above that point. You're going up the hill. So how much work was done by your engine? Work is change in energy. Not kinetic, not potential, mechanical energy. The work done by your engine now, I'm neglecting the friction, by the way, otherwise I have to deal with the friction force. Subtract that. That's coming up next. And thank goodness we have a friction, because if you don't have any frictions, you're not climbing that hill. But I'm neglecting it for this example. It's change in energy, which is the final energy minus the initial energy. When I say final, I'm talking about combination, potential and kinetic. Minus the potential and the kinetic of the initial one. What is my potential energy? It's the mass. We never give you a mass for the car, right? Your car is what, 1,300 kilogram? So it's the mass, gravity times height, final, plus 1/2 mv final squared, minus mass, gravity, initial height, plus 1/2 mass v initial squared. I need to convert my speed from miles per hour to meters per second. You divide by what? 2.24? So 50 divided by 2.24. So you're going here, v initial is 22.3 meters per second. Your V final, 60 divided by 2.24, 26.8. And now let's plug in the numbers. The mass is what? 1,300. Gravity is 9.8. Final height. What was the final height? We just calculated that. 13 meters plus 1/2 1,300 times final velocity squared, 26.8 squared. This is the final. Minus, let's do the initial. The mass, which is what, 1,300, Gravity 9.8. What was the initial height? 0. Plus 1/2, 1300. What was my initial speed? 22.3 squared. Do the math, and that's how much work your engine did if we neglect the friction and wind resistance. If I push all the right button on my calculator, my final answer is 309,238 joules. Or 3 significant digit, that'll be what? 3.09 times 10 to the power 1, 2, 3, 4, 5. Remember the equations for free fall when we did the free fall? We don't even have to use them anymore. We can still use them. I can use conservation of energy here because gravity, conservative energy, which means if you look at the sum of potential and kinetic at any given point on that path, they will be the same. Meaning what? We did a problem like this. Somebody standing on the diving board here. We'll do actually this both ways. Somebody standing on top of a diving board. How high you want the diving board is? Pick a number. 15?
Yeah.
Okay, you're trying to kill everyone today. Okay. It's all right, 15 meters.
How high is that? Like,
About 50 feet. It's not undoing. That's, you see him at the Big E. Yep. We'll use the wire as reference. He steps or she steps off the diving board, which means what? When I say steps off the diving board, what was the initial speed up there? If you just step off it, that's 0. Can you tell me how fast, what was the speed when this person enters the water? When he or she hits the water, how fast are they moving? What's their final velocity? Here's what I know. My initial speed is what? 0. If I use the water as reference, what's my initial height? 15. What's my final height? 0. What's the acceleration? 9.8, right? Negative. What's the final velocity? Do you have an equation that will tie all these together? Equation 5, right? I can use that. And notice when I'm doing this, I'm neglecting the wind here. The wind resistance, I'm neglecting that. Neglecting friction. Friction is not a conservative force. You lose actually force due to friction. Conservative force, we said you don't lose anything. So my final velocity, that's what I'm looking for. Initial velocity is 0 squared. 2 times gravity negative 9.8. Initial height or final height is 0. Initial was 15. 294, and you take the square root of that, and we'll say negative. Negative to indicate is coming down, right? Because you'll be coming down to the water. So the value is going to be the square root of that 294, and the minus sign just tells me it's coming down. So you're going to hit the water at almost 38 miles per hour. Don't land flat on your back there. You're in trouble there. At 38 miles per hour, you will feel it. Now, I'm going to do this problem. I just want to show you the answer is not going to change using conservation of energy because I neglected the friction. Friction is non-conservative force. The only thing acting on this is gravity, and we say gravity is a conservative force. That means if I take the potential and the kinetic here on the top, we know the initial speed is what? 0. We know the initial height is what? 15. Right at the bottom here, we know the final height, which is what? 0. What is the final speed? Unknown. We're looking for it. Now, since you have a conservative force, it says if you take the energy, the total energy at the top, mechanical energy at the top, it should equal the mechanical energy at the bottom. If you calculate the potential at the top and the kinetic energy at the top, if you add them, it should equal the potential energy at the bottom plus the kinetic energy at the bottom when you have a conservative force. Anywhere along the path, at any spot along that, the sum of potential and kinetic will equal to that, will equal to this. They'll equal each other at any given point on that jump there. Well, what is my potential energy at the top? Isn't that the mass? I will give you the mass of the person, that's okay. Gravity is what? 9.8. What was the initial height? 15. The kinetic energy is what? 1/2 the mass, which is what? M. And what was the velocity at the top? 0 squared. Should equal. Let's look at the bottom. Bottom, potential energy, which is mass, times gravity, 9.8. What was the initial height? I mean the final height? 0. Plus the kinetic energy, 1/2 m velocity squared. I know this piece is 0 because you're multiplying by 0, and I know that piece is 0. That tells me when I do the math, m times 9.8 times the 15 should equal 1/2 m v squared. What happens to the m's? Cancel each other out. V squared will equal, you multiply by 2 to get rid of the fraction, 294. Same answer as this. And what is V? It's going to be negative because it's coming down 17.15 meters per second. I think that's a little bit easier than this. You can use it for projectile. Soccer ball getting kicked. I don't have to break it down to X and Y components. This will tell me what the value is. I can tell you how high an object will go. Now, when we design roller coaster, they're designed based on that logic. You know? Because really there's minimal friction between the track and the roller coaster. So when you look at the roller coaster there, or a water slide, what do you want, a water slide? Here's the water slide. You're sitting up here, again, the same thing. And you're going to come flying down here. And the question, what's your velocity right here? Let's give you some height here. How high this point from this? I don't know. What is a water slide normally? How many meters? 2 meters high maybe? How fast are you going to be moving? At the top, you're sitting there. You're holding on the edge there. Hopefully there's water running under you. What's the purpose of the water under you? Yep, minimize the friction. If you ever try to slide down water slide where there's no water, by the time you get to the bottom, you'll feel, especially if you're wearing shorts or bathing suit, you'll feel that the heat and everything is dragging probably the bathing suit in pieces now. Friction. So the water actually minimizes the friction. Neglect friction here. We'll bring in friction shortly. Neglect friction. Your initial speed here is actually 0. If I use this point as reference, I don't care how high above the water that point, but if I use it as reference, if I take the potential and the kinetic at the top, it should equal to what? The potential and the kinetic at the bottom. And the nice thing about this, it really doesn't matter if you're a skinny person or a big person. The mass is not a factor. You'll see that. So the potential is what? Mass, gravity, 9.8, and what was the height? I'll put the equation for the potential in case you forgot. mgh. Kinetic energy is what? 1/2 mv squared. So let's look at the top. Potential. The mass, unknown. Gravity, 9.8. What was your initial height? 2, right? We're talking about the top. 2. Your kinetic energy. It's 1/2 your mass times your velocity square. What's your velocity square? 0 and square it. At the bottom, potential energy, that's mass, gravity 9.8, and what's the height? 0, good. What was the kinetic energy? 1/2 the mass times the velocity squared. And again, the ones with 0 in them, they will go to 0 because you're multiplying by 0. This is 0, that's 0. What's left? 19.6 m equals 1/2 mv squared. You can cancel the m from both sides. That's why I said the mass is not a factor. Multiply by 2 to get rid of that. (39.2) equals v squared. V equals the square root of 39.2. So when you come out of that end, is it 6.3? .3 meters per second. That's how fast you come out of that end. And the question is, what about if we make that roller coaster like this, or the water slide, because the kids don't like height, like this? How fast you'll come out of this end? Same thing. And what about if we make the go like this? How far you come out of this end? How fast? Same thing. So how do we design it? Has no effect on how fast you can come out of that end. Because we still look at the potential and kinetic energy at each one. Top, potential and kinetic doesn't change. The bottom, potential and kinetic doesn't change. The actual design of it, it's really not important. Does it go straight down? Does it go a little bit slowly? Does it zigzag like this? You know?
Potential energy, when it's at the bottom, because I've noticed on the last two problems, you canceled out the gravity,
Yeah, because the height is 0. I'm using this as reference.
so there's no gravity involved.
Well, if you put 0 here,
Okay, so
yep, that's what happened to that one. If I use the water as reference, I need to know how high this is above the water. But then in that case, this will be what? Will be this plus this. Mathematically, it won't make any difference. You know? It doesn't change anything mathematically. As I said before, the roller coasters are designed really on this logic. You go on the roller coaster, it will look like this. Then you get another piece here, you know? And if I use this as reference here, and let's say, I don't know, this is a steep one here, 50 meters high. And let's say this is here, 20 meters high. I can tell you how fast you are moving here and how fast you are moving down here. I can tell you your speed. Because on the top, if you see in the roller coaster, it barely moves. So we can approximate that by saying it's 0. Or we can measure the speed of the top here. It's not that difficult. But you're really barely moving. So you can round it. You know what? The initial speed is 0. Let's make life easy. And we assume neglect friction. So if you neglect friction, if you take the sum here, we'll call this point A, we'll call this point B, we'll call this point C. The energy at A, the sum of it, should equal the energy at B, which should equal the energy at C. At anywhere on the track, the sum should be the same. So if I'm looking for the speed at B, I go, what's the sum at A? We have potential energy plus kinetic energy. At B, we have potential plus kinetic. At C, we have potential plus kinetic. C, I mean. Let me focus on B first, then I'll add C to it later. Potential energy mass, I didn't give you the mass again because it's not a factor. Gravity is 9.8. The height is 50. Kinetic energy, 1/2 the mass. Velocity squared. Here, potential energy is not 0. You're on the top here. Your potential energy is mass times gravity times the height, which is what? 20? I put 20 meters. You see it? That's 20. Plus the kinetic energy now we do the math. This piece is 0 because 0 times anything is 0. 50 times 9.8, 490 m. 20 times 9.8, I think is 196 m. 1/2 mv squared. That's the velocity at B. I'll go VB, the velocity at point B. Notice every term has an m in it. Mathematically, I can just take my eraser, erase the m's out. That's dividing every term by m. So now you have 490 equals 196 plus 1/2 the velocity of b squared. Bring this one to this side, becomes a minus. 490 minus 196. 294 equals 1/2 VB squared multiplied by 2 to get rid of the fraction. 588 equals the velocity of B squared. To get the velocity of B, what do we do? Square root it? Take the square root of 588 and you move in 24.2 meters per second. So you go about 55 miles per hour at the top here, based on my picture. 50 meters, a good drop there. So you go about 50 miles per hour up there. When you get to the bottom, if you think that's fast, wait till you see when you get to the bottom how fast you're moving. Now again, when they design these, they got to make sure that you're moving fast enough, because why? If you're moving too slow, the weight is going to be pulling down centripetal force backward in that direction. If you're not moving fast enough, you're putting a lot of pressure on these wheels to hold you on the track because you're pulling down on it, and it might not make it to the top and you're stuck there. So you have to make it fast enough to keep it on the track going on the outside. That's why the radius becomes a factor. Because if you look at the top here, you want mv squared over r here to be that value at least equal to the weight down, which is what? Mass times gravity. It has at least to be equal to that. If this one is larger than that, you're constantly pulling on the track. If this is much, much larger than this, you're constantly pulling on the track outward. So we don't want to I want to make sure this force is not too much bigger than this. Because if it is, if it's 10 times this, every day, all day long, you're pulling with the force like 10 times larger on the outside. Like somebody has a chain attached to it, tied to a truck, and you're pulling on it. Eventually that thing is going to snap from wear and tear. So you don't want that force to be much, much larger than this. You want them close to each other, maybe just a hair bigger, but not a lot. You don't want to have a large force pulling in either direction. If this is much larger than this, you're not going to make it up the track. You will never make it to the road. You go up to here, then you slide down, you're stuck right there. If this is larger than this, you will go around. So the m will cancel each other out. So you'll have v squared over r has to equal to g. And we know what the velocity is. I can tell you how big the radius for that track should be to make sure that force is just a hair bigger than this. So when they design, it's not just, oh, let's put a loop there. Somebody sat there and figured all these values to make sure actually we're not putting too much stress on that. Now, can I find the velocity at c? Sure, I can set a equals to c. If I do a and c, at A, we know it's the potential and the kinetic. I have them right here. Mass times 9.8 times the 50. The kinetic energy is 1/2 m times 0 squared. At C now, if this is my reference, what's my height at C? 0. And my kinetic energy is 1/2 the mass times the velocity at C squared. So now I can tell you how fast the roller coaster will be when you hit actually the bottom there. At that 20-meter high, it was going 55 or 54 miles per hour. Let's see when you hit the bottom, how fast you're going. And I can cancel the m's out. Multiply by 2 to get rid of the fraction. So 2 times 490, it's 980. And what is VC equal to? 31.3 meters per second. approximately you're going on the bottom, approximately 70 miles per hour. At the 20 meters, we said you're going approximately, what, 54 miles per hour? Here's 70 miles per hour when you hit the bottom. Then you gotta stop quickly. Right there, you're gonna stop quickly. You have that distance to go from 70 miles per hour to 0. What caused you to stop? Friction. You ever see how they work the friction on this roller coaster? It's a piece of metal. It rubs against that metal. As you go tighter and tighter and tighter, that's how they slow you down. Runaway trucks, how do they stop them? You seen them? Actually, if you're coming from Lee, Mass, on the highway, going uphill, what they have? Sand in it. Sinking in the sand. The sand becomes the friction, slowing you down. You don't need fancy brakes for that. That's all you're doing. So we neglect friction the whole time.